Hello, this is video 3.5, Operations with Matrices. Just let you know that the next two videos will be pretty long. All right, so we're introducing matrices. In this concept, we're going to analyze the data in matrices, and we're going to perform some algebraic operations with matrices. So let's look at the vocabulary. What is a matrix? A matrix is a rectangular array. Array just means arrangement of variables or constants or both in rows and columns, usually enclosed with brackets. So here you'll see a picture, an example of one of them. Now an element is each value in the matrix, and each element has a unique position of the element written with the letter of the matrix, with row number and column number written as a subscript, and we call this the address. So when we're talking about the address, all right, so we're going to, for instance, it's always going to be the element, I'm going to call it E, with the subscript RC. This order is important. R is going to stand for the row, the number of the row it's in, and C is going to stand for the column. Okay, this is going to be important when we are identifying a matrix and finding its size. We've got to know it's always going to be row, column. So same thing with the address. So they go hand in hand. All right, so let's look at this example. Look at number -1. That element is -1. It's in row. Our rows go this way, row 2, column 1. So its address is going to be A, because A on the outside is the name we give to the matrix. Just like we gave names to equations and functions, we're going to give names to matrices. So this one's A, so we use little a with subscript 2, 1. This means it's in row 2, column 1. Look at number -8. So it's going to be A, row 3, row 3, column 2. So it's going to be A, subscript 3, 2. Now, the dimensions are the size of a matrix. How a matrix is described and how we describe and name it is always going to be row by column. So, for instance, this one's got 1, 2, 3 rows. So it's going to be a 3 by, and the number of columns is 1, 2, 3, 4. So this would be a 3 by 4 matrix. And it's going to be really important that order matters. So it's read M times N, where M represents the number of rows and N represents the number of columns. So it's important to know it's M times N, or R, which represents R and C. Okay, scalar is just a constant that we use to multiply by a matrix, and we're going to learn more about it as we get into the lesson. Scalar multiplication is the actual operation of multiplying each element by a scalar. So let's start in the beginning. Let's look at example 1. It says the manager at the Miami location would like to use their matrix to further analyze the representatives. So here they're giving us the position of jobs, their wages, and the cells, and this regards to the Miami location. If you look at the very beginning, it starts off and talks a little bit more about this. So an entry-level position makes $900. An assistant-level position makes $2,400. And an associate makes $2,700. Now how many cells they bring in? An entry-level brings in about $145,000 of cells. Assistant $225,000, associate $290,000. So this is a matrix. We've got 1, 2, 3 columns by 2, so it's a 3 by 2. Okay, so let's just basically this first example is just analyzing the data. So we're going to add the elements in each of the columns and interpret the data. So if we add the wages, we're going to get $6,000, 900 plus 2,400 plus 2,700. And then if we add the cells, we're going to get a sum of 660,000. What does that mean? Well, in column 1, that's the total average daily wages of the 3 types of employees that the location has. Column 2 is just the total average annual sales of employees. That's it. It's just a total. So B says the manager wants to determine the average sales for all of the employees at the Miami location. He decides to divide the total of the first column by 3, the number of different positions. So what is the average? So we said the total was 6,000. So we're going to have 6,000 divided by 3, and we're going to get $2,000. Okay, the next question, is this an accurate average? Explain. Well, if we have the same number of each type, then yes. Otherwise, it's no, and it would need to be weighted. Okay, I'm not going to expect you to do this or do this kind of stuff. I just need you to interpret what the matrices are telling us and what we can use the information for. Would adding the rows provide any meaningful data for the manager? They're saying what we just did, adding each row from each type together, no, it's not going to do us any good because the wages have really nothing to do with the cells other than the position. So can we compare wages and cells? No. So in this particular one, it'd be no. All right, so let's go into the operations. So we've got 4 operations in math, and we're going to start off with adding and subtracting. To add and subtract a matrix, we've already discussed how do we determine the size and identify the matrix. It's going to be m times n, or the number of rows times the number of columns. So to add or subtract 2 matrices with the same dimensions, we would add or subtract their corresponding elements. Now I want you to write this down. I'm going to check for this in your notes. When we're talking about corresponding elements, we're talking about elements that have the same address just in 2 different matrices. So here we're giving this first set of matrices is matrix A, second is B. So what you need to write down for your notes that I will be checking is address or position is what corresponding elements are, and they must be the same. Example, the address of A12, which would be this A, would be added to B12, and there's how we get A plus 1, and it's going to have the same address. So what I'm looking for on the notes, besides that address or position is the same as corresponding elements, and they must be the same, is A12 plus B, we're talking about elements 2, is equal to C12. It's going to live in this, you see they all have the same address, but this is going to be our new matrix, and we're going to call it matrix C. And we use little variables to identify that it's a matrix, and we're not talking about the column. Okay, so that's what I'm going to be looking for. So let's go look straight into the examples and see what we've got going on. So it says find each of the following for A. Here's matrix A, matrix B, and matrix C. So they want us to do A plus B. So the first thing we're going to do is we're going to write them down. We have 16, 2, negative 9, 8, and we have 4, we're going to plus, negative 4, minus 1, minus 3, minus 7. First thing we want to ask, this is a 2 by 2, and this is a 2 by 2. Are they the exact same size? Yes, they are. So then we can add them, and the result is C, and it's going to be the exact same 2 by 2. So we're going to take 16 minus 4 is going to go here, 2 minus 1, negative 9 plus negative 3, and 8 plus negative 7, which is going to result in 16 minus 4 is going to be 8, and 2 minus 1 is 1, and negative 12, and 1. And this is our answer. This is matrix C. All right, so the next one, B, they want us to do B minus C. So we're going to find matrix B. We're going to write it down. We're going to minus C. Remember, we still have to do order of operation. So this is a 2 by 2, and this is a 2 by 1. Okay, to add or subtract, the rule is they must be the exact same size. Are they the same size? No, so this is not possible, so there is no solution because the dimensions are different. All right, so next they want us to do B minus A. Okay, B minus A. Matrix B is -4, -1, -3, -7, minus 16, -2, -9, and 8. Okay, we have a 2 by 2 and a 2 by 2. That leaves us with a 2 by 2 for matrix C. So we're going to have -4 minus 16, -1 minus -2. Don't forget, this is not the same as this negative here. -3 minus -9, -7 minus 8. And if you're not familiar, if you're not really strong on your sign numbers, it's going to show up here. And it's going to be really important because if you can't do sign numbers, you can't do matrices. So this is our result is, whoops. I got a wrong number somewhere. -1. Oh, this is +2. Sorry. So this becomes just -2, which is -3. I wrote it down wrong. So this is our solution. Okay, so they have to be the same. And then you just take the same elements. This element, so this is B. This is A, is going to be little b, and it's in row 1, column 1. And we're going to subtract it from row, this is A. So little a, 1, 1, which is going to go in little c, 1, 1. And you see it's in, so B11 is -4 minus A11 is 16. The result is -20, and it's going to live in matrix C, column 1, row 1. That's really important that you get that straight. Go ahead and pause it and do guided practice 2A, 2B, and 2C. Now let's look at multiplying by a scalar. We said a scalar is a number that we can multiply a matrix by. So this is important. To multiply by a scalar, K, multiply each element by K. So we have a matrix of 2 by 2. We're going to take the scalar at K and multiply by each letter. So it's going to be Ka, Kb, Kc, Kd. For example, our scalar is -3. We have a 2 by 2 matrix, so we're going to multiply -3 by every element in the matrix. Now notice how it's written. It's important to know this, that we could write K with a dot A, Ka, and it means K for a constant times some K is a scalar times any matrix. So let's look at example 3. If R is this matrix, find 5R. So our scalar is 5. You need to be able to identify that R is the matrix and 5 is the scalar, because these are going to be true, false on your test. Or multiple choice or fill in the blank, some sort. All right, so we can write 5, which is our scalar, -12, 8, 6, -16, 4, and 19. So basically, we're just multiplying 5 times -12 is -60, 5 times 8 is 40, 5 times 6 is 30. 5 times -16 is -80, 5 times 4 is 20, 5 times 19 is 95, and they stay in the same position. They don't change addresses, they don't move, they don't leave their house. Think of their addresses and where they are in the matrix is their house and their position. Okay, do guided practice 3 and pause the video. So now we're going to look at some key concepts, some properties of matrix operations. So for any matrix A, B, and C, for which the matrix sum and the product are defined and any scalar K. So the following properties are true. So if it's defined, then the commutative property of addition A plus B is equal to b plus a, just like the commutative property of addition for real numbers. The associate property says you can group. If you've got a plus b grouped together plus c, then you can regroup it and go a plus b plus c and change the order. Now, this is really important that you get this down. This says left scalar distributive property and right scalar distributive property. Basically, it says when you have a scalar k times the sum of two matrices, you can distribute that k times a plus k times b, so you can distribute and do the scalar first and then add them. Likewise, if the scalar is on the right side of the sum of the parentheses, do the same thing. So it doesn't matter, this implies multiplication. If you have the scalar on the left side of the parentheses or the right side of the parentheses, you can still distribute. Please know the difference between left scalar distributive property and right scalar distributive property. Let's look at example 4. So if A is this matrix and B is this, find negative 4b minus 3a. So what we're doing here is we have multiple step operations. We still follow order of operations, PEMDAS. So let's write our problem out first. So this is what we have, negative 4, negative 8, 2, negative 3, minus 3 times, remember this, anything outside of a symbol of inclusion implies multiplication, but we have to be careful, just like absolute value and greatest integer function, they actually had operations. Here it's multiplication, so there's nothing to do inside here because that's just our matrix. So we can distribute, it's a scalar, so this becomes positive 16 plus 32, and then negative 8 and 12. Now I'm going to write this negative, and my scalar is just going to be positive 3. Okay? I'm going to keep this here. So I'm going to distribute positive 3, not negative 3. If I did negative 3, then I would have to change this to plus. Okay, so 3 times 9 is negative 27, 36, 6, and negative 18. So what I'm doing is I'm taking 3 times this, and it stays in the same address. 3 times this goes here. 3 times this goes here. 3 times this goes here. So now I can subtract it. Well, I have a 2 by 2 and a 2 by 2, so it's possible I end up with a 2 by 2. So I'm going to take the same position, 16 minus negative 27, 32 minus 36, negative 8 minus 6, and 12 minus negative 18. So what I'm doing is I have to stay in the be corresponding elements, meaning they live in the same address, but just of two different matrices. And then the result is going to be in that same position. So then I have 16 plus 27, which is 43. And then I have 32 minus 36 is negative 4. Negative 8 minus 16 is negative 14. And 12 minus negative 18 is positive 30. And that's how you would do multiple step operations. So we did the subtraction piece of it, like we did earlier, and then we did the scalar. Now we're putting them together, and just like we do in order. We start off with just adding, subtracting, and then we put it all together. So go ahead and stop the video. There's one more guided practice you need to try, which is number 4, and then we'll see you in class.